talked about flux of B field. If the B field is uniform, the flux is the B field times the area times cosine of the angle between area vector and the B field. And that also can be written as B dot A. And then if B field is not uniform or the surface is not flat, we say phi B is equal to integral of B dot dA. And then we talked about the fact that when the magnetic flux changes through a loop, a wire, it creates EMF in that wire. And the EMF created, we call it induced EMF, is rate of change of flux of magnetic field. And another way to talk about this is integral of E dot dF. And then we talked about motional electromotive force. A piece of wire is moved by the speed v through a magnetic field into the page like this and has length L, and magnetic field is B. It creates E and electromotive force of BLV. This is called motional electromotive force, which is consistent with Faraday's law because you can think of it as part of a loop. And when it moves, this area shrinks and flux through that loop decreases, and therefore we expect an EMF. And that EMF turns out to be BLV. And there are some energy considerations that I want to go over here. Let's say now you have a loop of wire and it is in uniform magnetic field going into the page here. Let's say this is your loop and part of it is in the magnetic field. The magnetic field only is here. You pull this away this way. So as a result, this area that has field in it shrinks down. And let's say you're moving with the speed v, it has a resistance R, and as a result there's EMF, and because of EMF and resistance there's a current going through it. Which direction is the EMF from Lenz's law in this case? You can say either counterclockwise or clockwise. Which one is that? First we say that the flux is going to the page and it's reducing, right? So the induced current is in a direction to create a magnetic field that goes into the page to support it because it's reducing, right? So then you use right-hand rule. Say if the field of the loop is into the page, then the current should be in this direction, clockwise. So it's like this, right? And the current will be EMF induced divided by resistance of the loop, right? And then now that there is current in the loop, there will be a force on each part of this loop. What are the forces? What is the force on this side, and on this side? That part is not in the magnetic field, so it doesn't have a force. Can you tell me what are the direction of the forces? So we are reviewing all parts of these two chapters, right? So now that there's a current here, what is the force on each side? We said the force is the current times L cross B, right? So on the top part is which way? Current is that way. Cross B, the force is up. So there's a force this way. Let's call F1. What about the bottom? Force is downward, right? F2. And these are the same, so cancel out. What about this one? L cross B, this way. So this is F3, right? So you are applying a force this way, F applied, and this is the force of magnetic field. We call it F of magnetic field, FB. And if you go at constant speed, it means that this force should be equal to that force, right? And then I is induced EMF divided by R. What is induced EMF? BLV over R. This is the current. And then the force is what? Force that you apply, or the force of magnetic field, either one. They are the same magnitude. How much are they? Is I L times B, right? Is ILB, I induced, L times B. So if you multiply this I by L times B, you get B squared, L squared, V over R. B squared, L squared, V over R. You have to apply this much force to move at the speed V in the magnetic field. Because you have current and you have resistance, how do you calculate the power? It's Ri squared, isn't it? Ri squared. I induced in this case. What is that? Power dissipated by the current is R times E L V over R squared. And so we get B squared, L squared, V squared over R, right? Because none of the R's cancel out. So the power is equal to B squared, L squared, V squared over R. But if you're applying this much force, how much power are you putting in? If you apply a force and moving at velocity v, what is the power for the force? Because it's doing some work, right? This is force times distance. Power of the force is the work over time, right? Work is what? Force times distance. I guess this force times the distance divided by time. Distance divided by time is F times V. In fact, in general, you can see that because this is force vector dot displacement. Displacement divided by time is velocity. It will be force dot velocity. If you're going in the same direction, it becomes just force times V. In this case, you're going in the same direction as the force. So the power from the force is force times V. What is the force? B squared L squared V over R times another V. Get V squared. And you see the conservation of energy. And the energy that is dissipated in the loop is the energy that whatever is moving it is putting in. That's conservation of energy. And the forces have to be the same if you move something at constant speed. To sugarcoat a little bit of this material, let me give you another example. Let's say you're not moving this by hand and let it fall under gravity. Let's say there's a magnetic field going into the page, and in this region of space, and then you have a loop of wire. The magnetic field is only in this region. It has a resistance R and has a mass M. So the gravity is pulling down by mg. And the size of this is L times H. What happens to this? The gravity pulls, and first there's no current, so it accelerates by exertion of gravity, but as soon as it starts moving, then induced current will appear. Induced current is in which way? Is it counterclockwise or clockwise? The area is reducing, therefore the flux that's going into the page is decreasing. The current wants to keep it constant, so it supports the flux. It is created in a direction where the magnetic field of that current is also into the page. So it goes like this, right? That's the induced current. And then what is the force on the sides? Again, and in this direction, the force is this way, and the force this way, right? F of B. And what happens is the acceleration reduces, right? As it goes faster and faster, this force becomes bigger and bigger. The speed increases until these two forces become equal, right? Then it goes at constant speed. Terminal velocity is when the net force is 0, right? Terminal velocity, mg, should be equal to fb. At fb, you can do the same kind of reasoning. fb is this, right? It's BLV over R. So mg equal to P squared L squared V over R. And now, if you solve for V, that's terminal velocity. Right? Terminal velocity is mgr divided by V squared L squared, right? Now look at this carefully. What does it say? If you have a non-conductor which has a very large resistor, there's no current being created. This falls very fast, right? The less resistance you have, the less this terminal speed will be. What if you have a superconducting wire? Means R is what? 0. Means what? It doesn't fall. If you have a superconducting wire, it gets locked in the magnetic field. That's why you see all these superconductors, they don't fall in the magnetic field. They get locked. Because superconductor has basically no resistance, so it doesn't let the magnetic field to change at all. Whichever way you want to change the magnetic field, it creates a strong current to oppose that. And you can make as strong current as you want because there's no resistance. So you see, resistance is 0 for superconductor, it doesn't fall. And that's why you see all these superconductors, they demonstrate superconductivity by suspending them in a magnetic field. Right? That is a simple example of that. And now what is the application of all of these? What do you think? Do you know the application of this Faraday's law?
Like generators?
Yeah, electric generators. You see all the lights that you're using, all the energy, electric energy that you're using is made by this Faraday's law. Except when you're using batteries, that's chemical energy. Either you're using chemical energy from batteries or you're using electricity from the wall that is created this way. In all the electric power plants, they have a loop of wire that is in a strong magnetic field. And then there's something to rotate this loop. When it rotates, the magnetic field changes in the loop, and that creates current. And all of these windmills that you see, I turn that coil with wind, or in Niagara Falls, for example, it's hidden down when the water falls, it turns some turbines, or they use nuclear power to create some hot steam going through some turbines to rotate the wheel. Any way they can rotate the wheel, they connect it to a loop of wire in a strong magnetic field. It creates electric energy. And also, this kind of induced current has other applications too. For example, if you have this coil of wire and it's sitting on a good conductor, like let's say this table was made of copper. If you put alternating current, magnetic field changes the flux into the conductor. Changing flux creates its own current. The current happens to be exact opposite direction with this current that is created, and then these two repel each other. And you can lift something with it. And all those magnetic levitation planes are using this principle. I think we have something here. This device is a coil with a large iron core. The alternating magnetic field created by the alternating current in the coil changes magnetic flux in the ring. The changing magnetic flux in the ring creates an induced current in the ring, which is in the opposite direction to the current in the coil at any moment. As a result, the coil and the ring repel each other like two magnets.